Class 7, Section 3.2, we're dealing with rigid bodies and equivalent systems of forces. Moment of a force about an axis. That's a long title. All right, so let's get to it. The bottom line up front, we want to learn about the scalar product. Maybe, hopefully, you already know about this. We covered the cross product in the previous class. Now we have the scalar product. And we also call this the dot product. And the idea, one of the reasons why we call it the scalar product, the idea here is we take two vectors and we dot them against each other, P dotted with Q. And what we end up finding in practicality is this is the projection of one onto the other, which is to say we multiply the magnitudes P and Q, and then we multiply by the cosine of the angle that's formed between them. Right? We could also take each of the individual components and multiply them by each other and add up each of those magnitudes, and that was going to give us the same thing. So we want to make sure that we're thinking of the dot product in these terms right here, and remembering that we're getting a scalar out of it when we take these two vectors and dot them. The mixed triple product, this is an interesting thing, and you notice the order of operations here, that we're going to dot some magnitude, right? Not magnitude, some direction, right? The direction cosine, this lambda right here. That's just a pure unit vector that's aligned with something that we care about. Well, we're going to dot that with a moment, and what we're going to turn out and find is we will get the moment that is about the axis that's defined by that lambda right there. So first, in terms of the orders of operation, we take the thing it's inside the parentheses, the RA with respect to B in this case. That's the position vector from the location of the, let's say here, we're taking A with respect to B. I said it backwards. This is where the force is located. Here's the position vector A with respect to B, and we're crossing it with the force that's passing through it. Now, if what we want to know is the moment that is that's caused by this force acting on here, but only the moment that's acting along this line, we dot it across this cosine, this direction cosine, lambda. So here's more specifics about this, and let me switch to my camera view right here and talk about and we go to my notes. And so here we have the scalar product right here, the dot product. And as I mentioned, what we're really doing is we're projecting one onto another. So we're really kind of taking this P and we're projecting how it affects, it goes onto this Q. Right in there. That's how we've always described it, is the P. And we notice that this is actually a commutative property, so it doesn't matter what order we do. We can also say that we're projecting this onto this one too. We're getting them in line with each other. And noteworthy things that happen, let's also have the distributive property. And noteworthy things that happen when we dot something against itself right here, we get 1. But if we dot something that's perpendicular, we get 0. So you see how that happens right here. So like if we're doing that, right, we can't project one of these onto the other. And we also know that the cosine of 90 is going to be 0. So these are all interesting traits that we want to kind of pay attention to if we happen to run across the dot product. And like as I mentioned before, we take each of these individual components and multiply them by each other and then add them up together. So one of the applications of this is that we could find what the angle is that's formed between two given vectors using both of these properties right there. So if you know all the P's and Q's, you can get this and you could equate it to this, and so you could take this and you could find the overall magnitude. These are the big magnitudes. Here's the individual component magnitudes, and you're able to find what theta is going to be. So that's a pretty useful trait. Let's see. So a very useful thing so what we can do when we want to try to I'm trying to speak out. I'm trying to think out loud here. 1 second. Let me pause my thoughts here for a second. Here, what could be very useful is if we have, like, say, we know a particular lambda of, say, this line L right here, and we want to find out what how much if this is some particular vector, and we want to find out what the magnitude of that vector is along that line. All we need to do is dot product P against this vector here, where we have the different direction cosines, right? And this is a unit vector. Remember that this is sort of like a localized unit vector that's specific to a particular orientation onto the thing. So what we can do is we can, if we know a vector, if we know we could turn it into this right here, and then by dotting that P, we will find how much of it lies against that L. So we don't necessarily have to have the P dotted with the Q. We might take and use the direction cosines to find out how much of the magnitude is projected out there. So here is an example. Sure, why not? All right, so here is this. We have this tension on this cable that we know to be 400 newtons. And we want to find out what are the components. So to find the magnitude of the projected component of the force along pipe OA. So we can get, and I said also find the angles too. That's probably a good idea. So we could find the angles that are in between this line and this line. We could find the angle in here. So what I'll start off with is I'll find the position vector of A with respect to O. That's going to be useful to us, right? So we want to find our A with respect to O. And that's just going to be from looking through here. And did I go ahead and leave these? I guess I left these the same, right? I said that in the x direction. Okay, so they're using x, y, and z. Hibbeler tends to do that right there. They make z the vertical axis, and I don't necessarily like that. But anyway, there's 0 here from A right there because they're in line with each other, and the x. And then in the y right here, the y is this direction. It's going to be a positive 4 because we're going over 2A from O. And then in the z direction, which is upwards, it's going upwards 6 meters. So there you go. There's the position vector of A with respect to O. Now we might also want to have the position vector of B with respect to O right here. Do I want to have that? Am I going to use that for anything? I don't know if I yeah, I guess I do. Yeah, I use it. I could also, by the way, find, what I did is I found B with respect to A. I could go that directly. So for some reason, I went ahead and did this right here where I went B with respect to O. And that's just going to be, again, x direction is 4. In the y direction, it's 5. And in the z direction, it should be 0, right? Yep, it is. So if I wanted to find our B with respect to A, what I could do is I could take our B with respect to O minus our A with respect to O, right? And I always think of these as sort of like indicinal math, like the indices right here. That we have the of O's is the common denominator, so we could that just turns into B minus O, or let's see, did I write it this way? I went 4 minus 0, 4 minus 0. I don't know why I'm putting parentheses in there. And then I have 5 minus 4. Yep. I should not have started recording this one this late at night. And then I have 0 minus 6. So it's just going to be minus 6, right? So my RB with respect to A is going to be 4I plus 1J plus minus 6K meters. And I could have done that, just I don't know why we bothered with this right here. We know that this is going over 4 from A. It's coming up right here. We could kind of tell that it's going to go 1 right here. It's moving over 1 from A to B, right? Because because that's 4 meters and it's 5 meters, so it's just 1 over there in the positive y, and it's going downwards minus 6. We didn't have to go through that step. I don't know why I did. So we can find what this magnitude is, this RB with respect to A. Find this magnitude. 4 squared plus 1 squared plus negative 6 squared is 7.280 meters, right? And then we could find the lambda of B with respect to A, right? And that's just going to be, that's just going to be this line right here, right? And facing downwards towards the thing. So that's just 4 over 7.280 I plus 1 over 7.280 J plus negative 6 over 7.280 K, or 0.5494 I plus 0.1374 J, and then plus a negative 0.8242 K, and there's no units in there. It's just the direction cosines. So if we want to define that force F AB, that's just going to be 400 times that. And a lot of times I'll just write that as anyway. So if all we have to do is take this and multiply it by 400, that multiplied by 400, and that multiplied by 400. So I just did it. I just went ahead and wrote that down. I just decided to be lazy. 54.95, and then that's up with a negative 329.7, and these are newtons. Now, I also, so when I want to get the moment, that's, do I want the moment? No. I want to project this thing onto that thing. So I decided that that's going to, that the vector that I want to project it onto is going to be O with respect to A, right? So it's got to go downwards right there. And that means that O with respect to A ends up equaling the negative of A with respect to O, right there, right? So that's just going to be 0, I, negative 4, J, and a negative 6, K. We could have always written that thing out there, and I don't know why we didn't from the very beginning. We were just playing around, I guess. And then we could also find that the length of this was the square root of 0 squared. Okay, that's right. That's great. Negative 4 squared and negative 6 squared. So what we're left with is 7.211 meters. So it's close to being the same length as that, not quite. And then, so if we want the lambda of O with respect to A, we end up with, this is going to be 0 still. And then plus, we have negative 4 over 7.211 J. And then we're going to have a negative 6 over 7.211k. So we end up with 0I plus negative 0.5547 J plus our negative 0.8321 K. All right, so if we want to find the projection of, find out the magnitude of the projected component of the force right here onto here, we dot these two things together. We dot that against that. So FAB dotted against lambda OA. And we would take the components right here. Take this 219.8 times 0. All right, so nothing happens there. Then we have 54.95 right here, and against this negative 0.5547. Then we take our negative 329.7, and we take our negative 0.8321, and what we find, we have 243.9 newtons is what the projection of this force onto that direction, right? So what we're in a sense saying is this thing is going to be in compression by that amount. That's going to be the amount that's pushing down along the length of that. And if we want to find the angle that's formed between these two, right in here, what we do is what we could do, okay, is take the use the direction cosine. It's probably the easiest one here, to take this and that and multiply by each other, because we know the magnitudes of both of those. That's easy enough to do. So I'm going to take the inverse cosine of the dot product of this and this, right? So that's just actually just the product of each of its components right there, right? So I'll write it out. We have 0.5494 right up here, and times 0, which was right there, and then add 0.1374, Homer Fimes, and then dot that against the negative 5547, and then take the negative 0.8242 and dot it against the negative 8321, right? And it's all going to be divided by 1 times 1, right? Because it's the magnitude times the magnitude, and the magnitude of this is 1, the magnitude of this is 1. And if we do that, we get 52.44 degrees, right? So that would be the angle that's between those two things. It's a little systematic thing. It's a good thing to know about. So that's long enough video. Almost 19 minutes long. Long enough.